Good morning. We continue our lecture on solidification of binary alloys. Now, we have so far looked at isomorphous system, its cooling curve. We also looked at the lever rule, which can be applied to find out the percentage phases which are present in a particular case. I mean, wherever you have two phase is coexisting. We also looked at the difference between an ideal and real solid solutions. We talked about free energy composition diagram in the case of isomorphous system. Then we moved over to cases where there is a solubility limit, that means two metals, they are not soluble in solid state in all proportion. In those cases, there will be a situation where three phases can coexist, and we looked at two particular cases, eutectic and peritectic system, and we looked at how the structure evolves in detail in eutectic and peritectic alloy. Now, we will continue for here onwards, and basically what we have seen that the transformation that takes place during solidification of a binary alloy is represented in the form of a diagram, which is called binary phase diagram. This is a graphical representation of phase compositions and their amount at a given temperature, and often we do it at constant pressure, and usually the pressure is 1 atmosphere. And one important condition here is we assume that the cooling is very slow, such that at every stage there exists an equilibrium between liquid and solid. And these binary diagrams, they are very useful tool for quantitative evaluation of the microstructure of the alloy, and hence it can also infer something about its mechanical and other physical behavior of the alloy. Now, in the case of an isomorphous system where there is unlimited solubility in both liquid and solid state, the freezing takes place over a range of temperature. We looked at this. We looked at eutectic system where there is a partial solid solubility, and here there will be at some stage a liquid which dissociates into a mixture of two solids alpha and beta. In phase diagram, we always represent liquid using this Roman alphabet L represents liquid, and Greek alphabets are used to represent phases. Now, we also looked at a peritectic system where, and this is also a case where there is a partial solid solubility, there is limited solubility in the solid state, but unlimited solubility in liquid state. And here under certain conditions over a range of composition, the liquid reacts with solid which has precipitated out to give a different solid, like in this particular case liquid reacts with alpha to give beta, where beta has an entirely different physical characteristics and structures from that of alpha. Now, these two cases, eutectic and peritectic, these are examples of invariant reactions, and in fact, at 1 atmosphere pressure, if three phases are coexisting in a binary system, that means binary system where number of component is 2, in that case if you apply Gibbs phase rule, you will find that degree of freedom is 0. So, that means this type of equilibrium can coexist at a fixed temperature and between a fixed composition of liquid and two solids. So, there is no variable that can be altered. So, in fact, in principle from the thermodynamic characteristics, it is possible to calculate these temperatures, and we will see today one such example. Now, there will be several other invariant reactions as well, which are possible apart from this, but basically similar to that, that one phase is separating into two phase or two phases reacting to give a third phase. So, this type there are certain other possibilities as well, and we will look at them in subsequent part of the lecture. And also we will look at some different variants of isomorphous system. First, start with this isomorphous system in the phase diagram. Just to recollect, this is the phase diagram of an isomorphous system, and in the two phase region one can apply phase rule, that lever rule. One can apply the lever rule to find out proportion of alpha and liquid which are coexisting. Like over here, the alpha of this composition given by that point P, that composition is x 1. So, this can coexist with a liquid of this composition x 2, and in this case, in using lever rule, you can say that alpha, amount of alpha is proportional to q r, and amount of liquid is proportional to p q. And there are certain alloys which exhibit this kind of phase diagram, which are listed here, like one of the common alloy is copper nickel, and here if you look at both copper and nickel, they have identical crystal structure, they have nearly similar lattice parameter, difference is less. So, therefore, atomic sizes difference is less. So, they exhibit unlimited solubility, and same I think will be valid, and for you to check up what are the crystal structures and lattice parameters of these cases, germanium, silicon, antimony, bismuth, but they also exhibit a similar isomorphous behavior. This kind of they will have, at least in the until solidification is complete, they will exhibit this type of phase diagram. Now, there are cases where this type of isomorphous system can exhibit maxima or minima. So, that means in between an alloy, there can be an alloy which has, in this particular case, higher melting point than both A and B, and which is shown in this diagram, and we will look at it here. Say suppose this is actually pure A, this is B, you have percentage B weight percentage plotted along this axis. This is melting point of A, here it is liquid, and here it is alpha. Now, here you have a maxima, but so that means you can look at it as if it is two isomorphous system, one this side, another this side. You can also have a case something like this, exactly similar. Here you have liquid, here you have alpha, and here this is pure A, this is pure B, this is melting point of A, melting point of B, and in between you have an alloy which melts in exactly same way as that of pure metal. If you try and plot its cooling curve of this alloy, it will actually be say temperature and time. Its plot will be more or less exactly similar to that of pure metal. So, this is the melting point of this alloy. Let us say this is the melting point, and it will exactly its solidification behavior will be similar to that of pure metal. So, this kind of deviations from an ideal isomorphous system, they are a result of deviations from ideal solid solutions, and we will later on we will see how we can express these deviations in a more quantitative fashion. Now, binary eutectic, we looked at eutectics, and in this particular cases where we have two phase alpha beta, these are terminal solid solution, this is liquid. Here you have alpha plus eutectic, here you have eutectic plus beta, and the two cases, there are certain case binary alloy system will exhibit this kind of behavior, like silver, copper, aluminum, silicon, lead, tin. They have this type of phase diagram, and this is a common solder alloy. This is used as lead tin is a solder alloy. It is a low melting material, and the type of structure that you can get in eutectic is shown here, and we can look at this. So, one type of structure in eutectic, say this alloy, here it is totally liquid, and once it solidifies, solidification is complete, you will have a structure which will give you really an intimate mixture of two phases, alpha and beta. Here suppose if say alpha solidifies, surrounding liquid becomes rich in beta. So, automatically the beta solidifies. So, in fact, one after the other it will start forming. So, you have a layer of alpha, on that a layer of beta will form, say something like this. If you have a layer of alpha forming, then within that you will have beta, then again alpha. So, this is way a lamellar structure can form. Similarly, you can also have this type of structure. If alpha is precipitates out, surrounding, if alpha precipitates out, surrounding is beta, again alpha precipitates out. So, you can have this kind of a very intimate mixture of this kind of a rod like this precipitate, which is schematically shown in this diagram, next one here. You can also have certain irregular structures are also possible, where maybe one phase is like this. Irregular structures are also possible, but what it means that eutectic will be an intimate mixture of two phases. Say this is say beta, this is alpha, and this pattern can be regular or irregular, and this depends on certain physical characteristics of the two metal A and B. Now, it is also possible to have one extreme case where the solids are totally immiscible, like here. This is a level diagram of a binary eutectic, where there is no solubility in the solid state. There are certain clear examples like cadmium bismuth, antimony lead, which exhibit this kind of phase diagram, and here the eutectic will be an intimate mixture. The hypoeutectic, you will have primary alpha, primarily that means A crystal of A and eutectics, and here in the hypereutectic alloy you will have primary B crystals of B and then eutectic. Now, using thermodynamics, it is also possible to calculate, if suppose we take the case of cadmium bismuth. If we know the melting point of cadmium and bismuth are known, the latent heat of fusion of cadmium and bismuth is known. In that case, if we assume that liquid is an ideal solid solution, it is possible to calculate from these thermodynamic data, that means melting point and heat of fusion, the composition as well as the temperature, that eutectic temperature and eutectic composition. It is also possible to plot this liquidus line as well as this, and we will look at one such example of calculating this type of phase diagram. In fact, we have seen one such example in the case of isomorphous system, where both liquid and solid are assumed to obey Raoult's law, that means both liquid and solid are assumed to be ideal solution. So, let us look at the determination of eutectic diagram from thermodynamic properties. Now, this is the problem. Bismuth, cadmium, they are soluble in liquid state, but insoluble in solid state. Estimates its eutectic composition and temperature. The melting points and latent heats of fusion of bismuth and cadmium, they are given below. Assume the liquid to be an ideal solution, and since pure bismuth and pure cadmium are precipitating out, we can assume that their activity will be equal to 1, and these are given over here. This is the melting point of bismuth is 271 degree centigrade, heat of fusion, that is enthalpy latent heat of fusion is 2.6 kilocalorie per mole. Cadmium melting point 321 degree centigrade, and its latent heat of fusion is 1.53 kilocalorie per mole. And let us see how we proceed with the calculation. So, here the main principle is that you have to calculate the free energy of this transformation, and look at a case in the phase diagram. Consider a temperature over here. If you are in this region, you have pure A in equilibrium. Pure A is in equilibrium with solution, that liquid consisting of liquid or a liquid solution of B in A. Now, how do you calculate the free energy of transformation, which is illustrated here? Say suppose in this particular case you take that pure A as standard state. In free energy calculation, definition of standard state is quite important, and we take the standard state, that is pure A at T, temperature T. Now, in this case, in that case, what is the free energy of pure A? See, since it is a mixture, it is R T ln activity of A. So, we write it mole fraction of A, and activity is equal to mole fraction. So, in that case this is 1, because it is pure A. So, this is 1. So, therefore, for pure A this is 0. Now, how do you calculate the free energy of that liquid, or let us say partial, we want to find out partial free energy of A in liquid. How will you find out? In that case, you take first pure A solid, it transforms into liquid, and then we assume that this A liquid goes into solution. So, in that case you can easily write it down. You can check up your earlier notes. In this particular case here, that free energy will be delta H of that melting of A times 1 minus T over melting point of A, whereas this is R T ln, we assume ideal solution to be ideal, then this is the atom fraction A in liquid. So, you add the two, this is the free energy. So, this is the partial molar free energy of A in liquid, and this should be equal to this. So, that is the chemical, that partial molar free energy is also known as the chemical potential, and this two potential should be 0. So, that means over this, if you sum these together, so you assume that this is some kind of a chemical reaction, and you add the two and they are in equilibrium. So, therefore, this two should balance, and with this what you get is listed here. In this particular case, you can say that atom fraction, the log atom fraction A in liquid will be a function of which is shown over here. So, this you can just algebraic simplification, this is equal to this, and you can apply the same concept to this region of the diagram, and then you get similar expression for this. Now, if here see all these are known, this is known, this is known, this is known, temperature is fixed. So, it is possible to calculate Na, that is composition of the liquid as a function at any given temperature T, and if you do that you will be able to generate this plot. In the same way, if you try and solve this, then you will be able to generate this plot, and wherever these two meet. So, this is where composition of the liquid which is in equilibrium with A is exactly same as the composition of the liquid which is in equilibrium with B. So, in this particular case the sum total of this will be 1. So, in this case that is how it is possible to find out the eutectic temperature as well as eutectic composition. And for this you can easily set it up in a spreadsheet, and these results which are shown here in the next one. So, these are the different temperature. This is the melting point of one of the two which is the higher, and this is in Kelvin, degree Kelvin, and you calculate that Nb, atom fraction B, and this is the other one, and if you plot the two, then you get, this is the diagram you get, and this eutectic composition comes out to be close to around, let us say 0.55 atom fraction, and this temperature comes out to be 408 degree Kelvin. So, in fact, if you check up this diagram, you will find that although there is a good match between this atom fraction, this composition is exactly same as given in the phase diagram, which is experimentally found out, but this temperature is possibly is a slightly lower, whatever we have found out by this. So, in that case, why is this deviation, why it is not matching? So, one possible explanation could be we have made an assumption that the liquid is ideal. Second is we have assumed that there is no solubility. So, now it is a question of is there a slight which is extremely small amount of A is soluble in B or B in A. These are some of the possibilities we can think about. So, that means you have to question these assumptions only, but the procedure, this is a procedure which is applied, and in one way you can say that thermodynamic properties are also evaluated from the phase diagram. So, actual experimentally you determine and then you try to conclude whether that liquid solution is an ideal or not. If it is not ideal, from this it is possible to calculate how much is its deviation from ideality. Now, next we also looked at the binary peritectic system. Now, binary peritectic system, this is one way you can when you look at the phase diagram, we said this is a very useful tool, by which you can know about the phase percentages, you make some quantitative estimates, like say in this particular case, say this alpha beta region, how will its property depend. Suppose we assume that alpha is softer, beta is harder. So, there is a possibility what we can say, you can apply that rule of mixture to find out its properties. So, if you know percentage alpha, it is possible to to find out the property of the mixture. So, suppose here we say that a particular composition, say on this we try and find out that on this axis we superimpose tensile strength or hardness. Say suppose beta has a certain hardness, say of beta of a particular composition. This composition has certain hardness, say let us say this is the value of this hardness, and then alpha has certain hardness. In that case, in this region, as amount of beta increases, if you go along this, it will follow something like this, a linear dependence. So, if you know percentage beta, you will be able to find out such properties. And also, if you look at the microstructure, say suppose if this diagram is not known, it is also possible to find out or locate this composition, these compositions from microstructure analysis of the microstructure. So, what you have to do, look at two microstructure or two composition, look at this microstructure, find out percentage alpha here, find out percentage alpha here, and in both cases, both the two phases alpha and beta, say here as it is shown here, they will have a composition, alpha will have this composition, beta will have this composition. So, using lever rule, you can set up one equation with these compositions, and secondly follow the second alloy, you can write a similar expression. In that case, and once you now have two equation, two unknown, you will be able to find out these compositions. So, it is both way possible. If the phase diagram is known, you can find out its properties from phase percentages, or else if a phase diagram is not known, but you find that this is the region, you have two phase structure, then you find out, at least make two alloy in the similar in the regime, and then find out percentage alpha and beta, and from that you will be able to find out the compositions, that is of the solvers, that is solubility limit of alpha and beta. And now, let us look at, we have looked at two types of invariant reaction. Say one is a eutectic, where liquid dissociates into a mixture of two different phases, two distinct phases having different physical and properties, physical mechanical properties, their crystal structure like alpha and beta. And we also have looked at a peritectic system, where two phases, say liquid reacts with alpha, giving a totally different crystal, say beta, a different phase called beta. So, these two cases we have looked at, but real phase diagrams are not basically not simple solid solution or eutectic or peritectic. They often consist of several two phase regions and invariant reactions involving three phases in a binary system. Now, this common invariant reactions, you have some invariant reactions other than eutectic and peritectic, and we will look at them. And we can broadly classify these invariants into two groups. In one case, one phase on cooling separates into two different phases, like that in eutectic, and another case, two phases on cooling reacts to form a different phase, like in peritectic. Now, let us look at the first group, that is one phase dissociating into two phases. Now, this example we have looked at in detail, say that is eutectic, and here this shows a small part of that eutectic phase diagram near that eutectic isotherm. Say like here, this is eutectic, you have two solid solutions alpha and beta, and this is the liquid, and this dissociates here. So, here it is totally liquid, and here it is a mixture of alpha and beta, and they are intimate mixtures. And now, we can extend this in cases where the liquids also can have solubility limit. There are several examples in liquid which you can think about. Try and mix oil and water, they do not mix. So, there is a possibility that there can be in these two phases, if you are trying to mix in the liquid state, they may not be soluble in each other, they may, and they may be partly soluble in each other. So, there can be several such examples, and let us generalize that we have a liquid and it dissociates into two different liquids having different composition. One we represent as L1 and another we represent as L2. And if we have a reaction, say one liquid L1 dissociates into a solid another different liquid, and which is shown over here. Here this is alpha, this is L1, and this side it is liquid is L2, and this is the miscibility gap. So, that means liquid here in this particular composition, liquid if it has this composition at this temperature, they will not mix, they are not totally miscible, they are not they will dissociate into two liquids L1 and L2. Say if you extend this, there may be a possibility that higher temperature chance of miscibility is higher. So, here they are miscible. If you go down this temperature, there is a miscibility gap, it dissociates into two liquids L1 and L2. This is a miscibility gap. So, in this particular case, this liquid is here, it is reacting, it is dissociating as you cool this temperature, is dissociating into alpha and other liquid, and this type of reaction is called monotectic reaction, or this is also an invariant, because you have three phases coexisting in a binary system. And you can have another variant, it is not that it is only liquid can dissociate on cooling into a mixture of two phases, you can also have a solid, say gamma, on cooling it dissociates into two phases, two other solid different solid phases alpha and beta, and this diagram is shown here. Say gamma is dissociating into alpha and beta. So, here, so this structure, say like eutectic, this structure you will call it eutectoid structure, and structurally also it will be very similar to that of eutectic. Say one very common example could be this type of lamellar structure, and this is called a eutectoid structure. Now, next is the second case where two phases react to produce a third phase. We looked at peritectic, where alpha reacts with liquid giving you beta, which is shown over here. Now, there are several variants of this, and from which you can derive in the same way as that from that eutectic reaction. And here, say like in this particular case peritectic, here you have alpha, this side is liquid, and here you have alpha and liquid, these two react and it forms a different solid solution beta. Now, you can think about liquid immiscibility, that means if there is a liquid immiscibility like this, the liquid here dissociates into two liquids L1 and L2. Now, these two can react and form a solid. So, this is a possibility and this is called syntactic reaction, and like eutectoid, it is also possible here also that two solid phases reacting and producing a third solid phase, and this is called peritectoid. So, here your solution, here this is alpha, this is gamma, here you have alpha and gamma coexisting in this region, and in this particular composition this two react and give you a different phase beta, and this part you will have alpha plus beta, this part you will have beta plus gamma. This is called peritectoid reaction. So, there are several of these I think there are possibilities, that means, and we looked at the common three phase that is reactions which are possible in binary systems, and each of these reactions involving three phases, they are invariant. So, they can take place at a fixed temperature, and it is possible that type of equilibrium is possible between liquids and solids, or between phases, three different phases of having definite compositions. So, that means at 1 atmosphere pressure. So, this temperature is fixed, composition of the phases which can coexist, they are fixed. And now, a real phase diagram, as has been mentioned, they will consist of may consist of several of these reactions. Now, let us look at some examples of construction of complex phase diagram. So, one example, say let us first take a case where we have to draw a binary phase diagram having one peritectic and one eutectic invariant reaction. How will you do it? So, in this particular case, so what you need to do, you have to say one eutectic and one peritectic. So, what you try, say you draw this diagram, say one you draw this isotherm first, say one peritectic, another eutectic. Say suppose we draw a peritectic here. So, this is a two phase, and similarly eutectic, that also will be at a fixed temperature, somewhere you draw this, then you have and then you try and join. So, this is so you may have to, and then you follow certain rules like the two phase region should be separated by single phase regions. So, this is, say suppose this is alpha, this is liquid. So, this is 2. So, this is 2 phase, and if you extend this line which is the boundary, single phase and a 2 phase, this should extend in this portion here. This cannot go to a single phase region. So, some of these rules you follow, and then it is possible to construct the diagram, and which is shown here. In this particular case, if you, this is pure A, this is pure B, this is liquid, this is one terminal solid solution alpha, and here alpha, this is a peritectic reaction, alpha reacts with liquid giving you an intermediate solid solution gamma, and this is a terminal solid solution beta, and you have an eutectic reaction isotherm over here. Similarly, let us take up a case, one monotectic and one eutectic reaction. How will you draw? I think you follow the same principle, and then you get a diagram, say one example. So, this part, this is monotectic. Now, if you look at this monotectic, now you should be able to level this diagram. I am leaving this as an exercise. So, these single phase regions, they have been leveled, but I have left out, say suppose you say that which is the liquidus line. So, liquidus line changes with composition, this top portion, this is the liquidus line. Similarly, what is the solidus line? So, solid, this part is solid, but here it is not solid. So, solidus, this is solidus. So, here this is the isotherm, this is a solidus line. Similarly, solvus, you can say these are the solvus line, this is the solvus line, and these are the regions of two phase region. So, this region is alpha plus beta, this region is alpha plus L2, this is L2 plus beta. Now, let us take up a case where there is one peritectic reaction and one eutectic reaction and another eutectoid reaction. You have 3 isothermal reactions. Now, how do you synthesize this? So, one example which is given is this. Now, these are the single phase region which have been leveled. I leave it to you to level the other. So, this is one peritectic, it satisfies that peritectic. You have one eutectic, this is the eutectic, liquid dissociating into gamma and beta, and this is an eutectoid reaction, a gamma dissociating into a mixture of alpha and beta. Now, when we look up some of the real system, you will see that some of the cases you have diagrams very similar to this kind. So, we have looked at eutectic, peritectic, monotectic, eutectoid. Let us try and try to draw a diagram where there is one peritectic, one eutectic and one peritectoid reaction. Now, this is one such case, this is pure A, pure B, and these are the single phase regime alpha, gamma, delta and beta. And you have 3 invariant reaction. This is peritectic, where alpha reacts with liquid giving gamma. This is eutectic, where liquid of this composition dissociates into 2 solids, gamma and beta, and this is peritectoid, where 2 solids, gamma and beta, gamma of this composition, beta of this composition react together to give you delta of this composition. Now, many metals they undergo allotropic transformations. So, at different temperature they have different crystal structure, and one common example we looked at is that of iron. So, there will be such cases in many binary phase diagram. You will come across such situation where pure solid also undergoes transformation, solid state transformation. So, a higher temperature it may have one crystal structure, at a lower temperature it has another crystal structure. As we have seen, pure iron, when you cool initially it solidifies into a body centered cubic structure, then it gets converted into a face centered cubic structure, and on further cooling it again transforms into a body centered cubic structure. So, that means pure iron has 2 such allotropic transformations. Now, how are these transformations represented in the phase diagram? So, let us look at one example where there is allotropic transformation. Let us say we have both metal A and B undergoes one allotropic transformation, and say I have not specified any of these previous phase diagrams, I mean when it just solidifies, but one example I am giving here. Say here first this liquid solidifies using say a simple say peritectic system, which is shown over here, and once it is solid it is gamma, but pure A which is solidifying here first as delta. It solidifies as delta and then again it transforms into alpha. Then gamma again transforms into alpha. So, pure A in this particular case has that solid A has undergoes one allotropic transformation delta to gamma at this temperature, and again from gamma to alpha at this temperature, and there is an eutectoid transformation at a lower temperature, where gamma dissociates into a mixture of alpha and beta. So, in this particular case, if you try and infer, draw the cooling curve of this pure metal, you will get one isotherm here, one step over here, second step here, third step here. Whereas, pure B you will get a one step for solidification and second step over here. Now, phase diagrams. So, with this we have looked at several types of phase diagrams. We have looked at isomorphous system with we also looked at some of these variations of isomorphous system, like one showing maximum, another showing minimum. We looked at eutectic structure. The eutectic structure can be some regular, say lamellar, rod like or irregular type of microstructure it can have, but nevertheless eutectic will be an intimate mixture of two distinct phases. Then we also seen that one particular case, that eutectic temperature, we have calculated eutectic temperature and composition from thermodynamic concepts. From free energy of transformation we have estimated for cadmium bismuth system. Then we looked at several invariant reactions, we looked at, and broadly these invariant reactions have been classified into two groups, that is one similar, one in which one particular phase is dissociates into two at a particular temperature, and the second category, two phases react together to form a third distinct phase on cooling. Then we also looked at construction of complex phase diagrams of several invariant reactions, and we also looked at representation of allotropic transformations. Now, here most of these diagrams for a binary system, you may wonder how are these determined, and here this we learnt about it in our initial classes under experimental techniques, and there we talked about thermal analysis in detail, and thermal analysis provides the basic primary tool for evaluation of phase diagram. You can recall that one is a simple cooling curve, and which we have been referring to in trying to find out how the structure evolves during solidifications. But there are better variants of thermal analysis, like differential thermal analysis or DSC, differential scanning calorimetry can be used, and so they give us accurate determination of these transformation temperature. That means, when solidification begins, when it is completed, when solid state transformation takes place, and apart from that also you can use any other physical properties also to determine phase diagrams, like you can do a resistivity measurement, anything, any physical property which is a function of crystal structure and composition will be can be used to determine the phase diagram. And we also have illustrated that one particular case discussing that peritectic phase diagram, that even simple microstructural analysis also can help you to identify the phase boundaries. With this we stop here, this today's lecture, and we will continue still with a couple of more classes on the binary phase diagram. I think next class we will possibly look at the deviations from ideality, the thermodynamics, and we also will look at what happens, because so far we were discussing the evolution of structure when the alloy is cooled at a very slow rate, where at every stage equilibrium is maintained. So, liquid, the composition change, it can easily adjust to composition change, because here the movement of atom is much faster than that in solid. But once a solid forms, solid, for the composition to change, you have to allow sufficient time, and if you do not allow that time, what happens? I think we will look into these in subsequent lectures. Thank you.